Okay. Hello and welcome everyone to this week's Infosys Chandrasekharan Random Geometry Colloquium. Today, we're extremely glad to have Pranab Sardar from IISER Mohali, who will give us a talk on geometry of hyperbolic trio spaces and Cannon-Thurston maps. Over to you, Pranab.
Okay, thank you. So I would like to thank Shubhajit and Mohanda for inviting me to speak here. So this talk is based on my recent book, Trees of Hyperbolic Spaces, jointly written with Misha Kapovich. So
Pranab,
yeah.
can you speak a little loudly or use a headphone? I think usually if it, are you using a headphone?
No, I am not.
If you use a, I mean, if you have a headphone, it's better to use it because then the sound becomes much clearer.
I see, but I don't have a headphone right now.
Okay, in that case, can just speak a little more loudly.
Okay. So the main theorem from this project is this is a new proof of this Bestvina-Feighn combination theorem that they proved in 1992. Namely, suppose pi from x to t is a tree of hyperbolic metric spaces satisfying QI embedding condition and always layering condition, then x is hyperbolic. So I will define the terms after some time. So this was a theorem due to Bestvina and Feighn, and we are giving a new proof of this. So the additional advantage of the proof is that we have some kind of a description of geodesics, quasi geodesics. So given a pair of points, there is some sort of description of a quasi uniform quasi geodesics joining this pair of points. And then in the second part of the book, we use this geodesics to prove that this following theorem that suppose we have the same tree of hyperbolic space x to t, and then you take a subtree s inside t, and let y be the inverse image of s. So you restrict your tree of space to subtree, and then the inclusion map from y to x. This admits Cannon-Thurston map. So a special case of this where s is just a point, a vertex inside the tree. So this was due to Mohanda, so in 1998. Okay, so I want to say a few things about this. So so I am extremely indebted to both Misha Kapovich and Mohanda for their generous input of ideas, without which this project was not possible. Okay, and so now I want to define all these terms that I have in this. So I thought initially that maybe I will prove theorem 1 and describe these paths, and then also indicate some proof of this theorem 2, but I think that will be too much. So maybe I will not have enough time for this theorem 2, so I will try to just give a proof of theorem 1 describing geodesics inductively like that. So let me explain the terms that are there in theorem 1. So what is a tree of metric space? So tree of metric space has the following data. So first of all, you have a tree. So you have a tree T, and then for every vertex V inside the T, you have a metric space XV, and for every edge inside the tree, you have some edge space. So so these are metric spaces. We call them vertex space and edge space. Okay, and so given this data, then we can form what is we may call the geometric realization of this tree of space. So namely, what you do is that so you so one more thing is that so there is a map. Okay, so for if I have two vertices v1 v2, okay, so then there is a map from I denote it like this maybe. So XE, XV, V1, and similarly V2. So I write I here. So I have, whenever I have two vertices connected by some edge, so then there are some maps. Okay. So given this data, so what I can do is that I can construct a different space. Namely, so you take for every edge, you take this xe and then take the product with interval 0, 1 maybe. Or in this case, I just write simply so interval 0, 1. Instead of doing that, I just write like this. So, okay, so this is a segment, and then I also take all the vertex spaces. So take the union of all this, and then do some quotient. So what I am doing is that I have this xv1 and xv2, and they are connected by some edge E. So then I'll take the x E here, cross 0, 1 interval basically, and then I'll glue this like cylindrical object. So this is simply this what I am drawing here. So this is x E cross this interval 0, 1 basically, and so the gluing from this x E cross V1, that point, to x this is given by this map f E comma V1, and similarly on this other side. So I do this for all the edges and vertices like that. So then I'll get a different space. Okay, and this you can think of this as the geometric realization of this tree of space. And so we'll assume that so this whole thing is a geodesymmetric space and so on. And then we also assume that the inclusion maps from the vertex space into this new space, let us call it X. So the inclusion maps, so these are proper embeddings. So these are uniform proper embedding. Okay, so this simply means that if I have 2 points in xv and their distance is less than d inside x, then inside xv their distance is less than d prime, where d prime does not depend on the points and the vertex v. So that's why uniform. So these are uniform proper embedding. So this is one of the conditions that we'll assume. And then there comes this QI embedding condition. So this simply means that these maps that I have written above, so these are uniform QI embedding. So some of the terms I will not define. So if somebody wants to know, then please ask. So these are uniform QI embedding. So that means there is a constant K and epsilon, so that all these edge to vertex space maps, these are K epsilon quasi isometric embedding, like that. So now, given this tree of space, so naturally there is a natural map from this X to T. So namely, you can collapse the vertex space XV to the point T, and then if I have some point X, some point of this XC cross this interval, so you collapse the corresponding okay, and then you will get a point inside it. So there is a natural map from this, and you can see this is clearly it is a ellipsis map. Okay, so this is a ellipsis map, a subjective map. Okay, and what is a QI section in this tree of space X? So what you do is that, so maybe you fix to what is this UE. Okay, and so here you have geodesic. So it's a tree. There is a unique geodesic UE. So a KQI section, it means that you have a map from this segment UV, geodesic segment UV into X. Okay, so here you have this pi. So maybe I call it S. So S is a map from the interval UV to X, such that what? Such that this is a KQI embedding this map. Okay. So S is a section of the pi, so it's a set theoretic section, and then this is a KQI embedding. That is the meaning of saying that this is a KQI section. And once you have that, then you can easily define what is called the Holly flaring condition. So what does it mean? So for every k bigger than equal to 1, okay, there exists some number nk and amk, such that the following holds. So suppose you have a geodesic segment inside the tree of length twice nk. Okay, so this is minus nk, and then you take two qi sections like this. Okay, and assume that this segment. So once you have qi section, so uh, so I'm just denoting this by integers minus nk 0 for convenience. So for every point here, okay, so there is the vertex space here. Okay, so inside the vertex space you have 2 points. Okay, for this maybe I call them I call it gamma 1, gamma 2, this section. So there is a point of gamma 1 and there is a point of gamma 2. So and that is sitting inside the same vertex space. So you can join them by geodesic segment inside the vertex space. So then suppose over this 0, this length is bigger than mk. Okay, so then what happens is that, so you consider the same thing, this length of this segments here and here. So maybe I don't know, I call it L minus and L plus. So then what happens is that the maximum of L plus and L minus is bigger than equal to 2 times whatever this, let us call this length L0. So L0 like this. So this is the Holly flaring condition. So for every k, we have to choose this nk. I mean, one gets this nk and mk like that. So this is the Holly flaring condition. So this explains all the terms in the theorem 1. So if I have a tree of space, and yeah, so I did not say hyperbolic. So I am assuming also that this vertex space and the edge species are all delta hyperbolic for some constant delta. So it does not depend on the vertex v and e. So a uniform delta works for everything. So all the vertex space and edge spaces are delta hyperbolic, and they satisfy this uniform QI emitting condition and this always flaring condition. So if all these things are true, then X is hyperbolic. So that is the this theorem 1. Okay, and okay, so I'll go on. If there are some questions, please ask. So the main tools for the new proof are the following. So number one is a criterion for hyperbolicity. So the Bowditch gives a characterization of hyperbolic matrix. Suppose so his statement looks a little bit different, but we can easily deduce this proposition from there. So what you have is the following. So suppose X is a geodesymmetric space, and I have set A inside X such that the R neighborhood of A is the full X. So we call it sometimes A is R dense inside X. So there is some constant R because then equal to 0 such that R neighborhood of A is the full X. And now suppose that you have a constant D and some function eta from 0 infinity to 0 infinity, and for every pair of points xy inside A, we have a rectifiable path. I'm calling it cxy. Okay, so there is a path inside X which is rectifiable. So X is a metric space here, so we can compute length and so on. So this is a rectifiable path such that the cxy, these are eta proper embeddings. So this again, so this means that, as I said before, so cxy this is really a curve, right? So you can think of this as a map from some some interval, okay, AB to X like that. So then these are eta proper embeddings. So if 2 points inside cxy are really close in X, then those 2 points are really close in the interval AB. Okay, and that is uniform, so it does not depend on xy. So some eta is there such that all of them work like that. Okay, and number 2 is that the triangles formed by cxy, cyz, and zx is slim. So this means that just like in the definition of hyperbolicity, suppose I have X y, and z. Then you have these curves. So this is cxy, cxz, and then cyz is there. Okay, so I'll not write everything. So then this is a delta. What is a d slim? So this means that given any side, let us say cxy, then this is contained in the d neighborhood of the union of cyz and czx, and similarly for the other two sides. So triangles formed by the cxy, cyz, and czx, these are d slim. Okay. So then x is hyperbolic, and then cxy are also uniform quasi geodesics. So this is the statement that that was given by Kapovich. So similar criterion is also given by Hamilstad also, but we thought that this is a little bit more economic. Okay, so we use this. So this is a number this is number one for the tools of the group. So number two will be Mitra's ladder construction. So this was a construction given by Mahan Mitra. So in his paper Cannon-Thurston maps for tree of hyperbolic metric space. So I'll come to that after some time. And also he defined cos ellipsis retraction from the whole space to the to these ladders. So he also had similar this object that he works with. So he had this tree of metric space, hyperbolic tree of metric space with QI embedding condition and so on. And so then he defines a ladder in that, and he also defines retraction from the interspace to the ladder. So so I describe all of this after some time. Okay. So these three things are the main tools. So this, especially this number 2 and 3. So these are used repeatedly. Okay, in the course of the proof. So what I'll so let me explain the overall idea of the proof of this theorem one. So the very basic idea is that the theorem. So for proving the theorem, what we want to really do is that so we want to apply the Bowditch's theorem. Bowditch's proposition. So for every pair of points, you want to define some paths, and then you want to check that the Bowditch's criteria are satisfied. So that is the basic goal. Okay, but in general, it may not be so easy to construct paths. So given a pair of points, any arbitrary points, it may not be so easy to find this path. So then what you do is that you work with some subspaces of this tree of space, which are easier to handle with, and for which you can easily guess what the paths are. Okay, so then you draw those paths and then you check these things. So this is the basic idea. So let me explain one by one these easy cases that for which one can easily define some obvious candidates for paths and then check these conditions. Okay, so suppose your tree is a very special one, so it's just an edge, two vertices and one edge. So this means that your space is looking like this. Okay. So suppose I have to connect 2 points. So then there are several cases that one has to consider, namely maybe the points are in the same vertex space. So in this case, what you do is that you just draw a geodesic. Okay, and similarly, if I have some point here and here, you just draw geodesic like this. And also, if I have I mean, this is not very interesting. So what is more interesting maybe is that so this is XU and this is XV. So if I have some point inside XU and some point inside XV, then what do you do? So then what you can do is that so this so there is this XC also. Okay. And so what is this? So this is really the image of the map F. So this is there will be maps, right? So from XE to XU, there is this map. So this shaded object this is the image of this map, and so all these things are hyperbolic. So therefore, it is easy to check that this is what is called quasi-convex. Okay, and so quasi-convex simply means that if somebody has not seen it, so suppose I have a hyperbolic space, something is quasi-convex means that if I have pair of points and I draw a geodesic joining this, then this path is contained in a small neighborhood of this set. So that is quasi-convex. So now for such things in hyperbolic metric space, there is what is called the nearest point projection. Okay. So given a point, you can choose nearest point. So that will be coarsely well defined. Okay. And one can check this is also ellipsis. So this using these two properties, so what you do is that given this pair of points, I'll project here, take a nearest point projection here, and then I'll just draw some horizontal path like this. Okay. And then I will join here by geodesic in XV. So these are all the candidate paths, and one can easily check that these paths will satisfy the properties of this Bowditch proposition. And in this case, therefore, this space is hyperbolic. The entire space is hyperbolic. Okay. So this is the simplest possible case. The next level of difficulty is what is called the strongly asymmetrical case. So in this case, you can choose any tree, okay, but the edge spaces are something very special. So namely, so given some vertex space X V, look at all the edge spaces, okay, that are going into this X V, okay. So these are quasi-convex. These are all uniformly quasi-convex. So we assume that these are what is called co-bounded, uniformly co-bounded. So that means if I take some, this is my edge here. So if I have to draw this, so maybe this is pi map. So I am looking at this kind of picture. Okay. So I'll give some name. So here maybe this is E prime and so on. So here this is so this image of X E prime, and this is image of XE. So they are uniformly co-bounded. This means that projection of this X, I don't know. So this, maybe I should have drawn it with different color. So this object, this red object, if we project on the black shaded this quasi-convex set, then the projection has a small diameter. And conversely, if I project the black thing on the red one, then the projection will also have a very small diameter. So the small means there is a uniform constant d that works, okay, for all the vertex spaces and for any pair of edge spaces that are going into this vertex space. So that is what is called the strongly acylindrical case. So in the strongly acylindrical case, what you do is that, so you suppose I have 2 points, okay. Suppose I have, so I draw something, so maybe here. So there is some vertex here, and then yeah, something like this. So suppose I have, I'll draw the inverse image of this. Maybe I'll give some name here. So this is EU. So this is XU, and this is X. This is W maybe. So this is W. Suppose I have some point in XU and some point in XW, and I want to connect them by some path, candidate path for quasi-geodesics. So then what do I do? So what I do is that, so I'll go to the next vertex space by taking a projection here. I'll take a projection here, and then there is this horizontal line, okay, and then I will project this point here, and in this way I go, okay, and finally I will come here, and then I arrive here, and then I'll just join these points like this. So this is the scheme of this. I mean, this is a way to get uniform quasi-geodesics. So one can easily check in this case that these paths will satisfy all the properties of Bowditch. So this theorem was also proved, essentially proved by Hammondstad, okay, and also it was proved in our paper, in my paper with Mohanda, so metric bundles, okay. But yeah, so but we did not give descriptions of quasi-geodesics there. But anyway, so this was already given kind of by Hammondstad, and although she did it in a special case where the tree was some interval or z, something like that, but one can do the same proof for any tree of this. So as long as you have the strongly cylindrical assumption, then one can show that these paths will satisfy the Bowditch properties, and therefore we have hyperbolicity, and these paths will be uniform quasi-convex. So one advantage of this is that nice thing about this is that notice that the vertex spaces are QI embedded in the entire space, vertex, which is not true in general. So in this case, strongly asymmetrical space. So this is so number one, you can see it is a special case of this strongly asymmetrical. So that was the this is a special case. Okay. Yeah. So any questions? Okay, so I'll go on. So next case that we consider the easy case is what is called what we have called in our book narrow carpet. So narrow carpet is a special type of tree or space. So where you have for the tree we have interval, some finite geodesic segment, and the vertex space edge spaces, these are intervals. So really the space looks like this. Like this, and narrow means so if the interval this is uv, so xu could be very large, but over the xb this segment has length small, so this has length less than equal to some constant d. Okay, and so there is a qi section. Okay, so really the tree of space is made up of this QI section. You have two QI sections and then you draw this geodesics. Okay, I mean the geodesics in the vertex spaces like that. So this is what we call narrow carpet. Okay, so here over the XU this length could be very large. We also don't restrict the length of this UV, this interval UV. But only assumption is that these are some KQI sections. So this is like gamma 1, this is gamma 2. So these are some KQI section. So therefore these are the parameter this K and D like that. Okay. Given that, so then this is hyperbolic, and this.
So this means that it comes D close at some point. That's what you're saying, right?
Yeah, that is enough. Correct. If that was the case, that would be enough. But I am saying just that we can look at this special case. That is also correct. Yeah. So if I have two QI sections and their distance somewhere is less than equal to d, then that will be hyperbolic, and geodesics will be easy to describe. Of course, I mean because this was already done in our metric boundary paper, and the description is same. And so now, how do I connect this any pair of points by geodesics? So maybe I'll draw with blue. So for variation, so maybe this x, and then some point y is here. Okay. So then what you see here is that so this space has a property that through every point there is a QI section. Okay. So that is not too hard to see because you see that. Let us consider 2 points which are adjacent. So maybe u1, u2. So over this I have this interval and some interval here, and here the length is small. So this is k, at most k, like this. Okay. And therefore the Hausdorff distance between this segment and this segment is uniformly small. Okay. So therefore through any point there will be a QI section. So you draw two QI sections through x and y. And here in the XV end, there this fiber distance is small. So just what you do is that you just look at the first point where these two blue QI sections are close to each other. Okay, so which means that yeah, so I mean one proves that through any point there is a uniform. Let us say if this gamma 1, gamma 2 were k, okay, and then you first show that through any point there is a k prime QI section, and then you refer to the flaring this hypothesis, always flaring. So then there is this threshold mk prime. So you just check when this blue QI sections through x and y they are coming close like within the mk prime. So you just notice that, and then you from x you go to that vertex, and then you jump from here to that QI section through y, and then you come back to y like this. So these will be candidate paths for the a special case when the trio space is a narrow carpet. Okay. So these are the cases where we can explicitly see what the paths are. Okay. And so I will say some more special cases and subspaces where we can still draw the paths. Okay. So for this, first I will introduce what we can call induced subtree space. So these are some special subtree space for which we are looking for paths, or explicit description of paths. Okay. So what is this? So suppose you have this tree of space X over T, and you have a subtree S. Okay. And for every vertex V inside S, you have YV inside X. So this is a subset of this. So, and YV, you can think of these as a subspace. Okay. And this is uniformly QI embedded, which means it is, maybe I assume it is path connector and everything. So it's a geodesic metric space with respect to induced Venn metric. And inclusion maps from YV to XB, these are uniform QI embedding. And similarly, YE. All these things are there. Okay. So you have the whole tree and you choose a subtree of that. And for every vertex of the subtree, you have this. Inside every vertex space XV, there is YV. Inside XC, there you have YE and so on. Now, you further assume two more things, so that I call complete or full subtree. So what is that? So suppose you have two vertices UV inside S, and they are connected by some edge E. It's two adjacent vertices inside S. So then YE is the coarse intersection of YE, YU, and YV inside this. Basically, if you just go back and check this, suppose when the tree of space has just two vertices, one edge, right? In that case, the vertex spaces are quasi-convex. Okay, and so now what I'm saying is that you look at this UV, okay, and inside there I have YU, YV. Okay, so these are quasi-convex inside your XU and XV, and therefore they are quasi-convex inside this XUV. Okay, this is hyperbolic. And so then, given this, so you can take what is called a coarse intersection. Okay, right? So given hyperbolic space and two quasi-convex set, I mean, that intersection can be very bad, but maybe you have to take a small neighborhood of that, and then the intersection is well behaved, so it will be again quasi-convex. Okay, and what I am assuming here is that this YE is uniformly dense inside this coarse intersection. So that's what I mean by saying Y. So it's like schematically. So you have these two sets. So this is your YU, this is your YV, and your YE is here. Okay, and in the coarse intersection, YE is uniformly dense. Okay? So basically, coarsely speaking, YE is really the intersection of YU and YV. Okay, like that. And second condition is that suppose I have a vertex V inside S, and I have some adjacent vertex, this picture, adjacent vertex W, but W is not inside S. So this is like a something going out. V to W, you are going out of this. So in that case, what is happening is that you consider the so you have this. I draw this here. So you have the XV here, and then you have this picture XW. Okay, and here you have YV. So this YV you project on this. Okay, this is what I said. This is what I mean. So this by this I mean the projection of XV on XE. Basically, I mean this shaded, this quasi-convex set. So consider this map, projection from XV to this shaded quasi-convex set, and apply it on YV. Okay, so then you will see that the diameter of this is smaller than D, some constant D. So these are all the given data. So when I am considering this induced subtree of space, I have all this given data. Okay, are there any questions? Okay, so once you have that, so then you can easily define Mithra's projection. What is that? So I have a subtree of space, induced subtree of space y inside X. Then I define a map P from X to Y. And how do I define this map? So basically, suppose I have some vertex V inside S and some point X inside XV. Then P of X, to define P of X, what I do is that I just look at the projection of this, maybe I should have called it, sorry, this is not correct. So I take the projection map from XV to YV, okay, and apply it on X, that's all. This is what I do. So you have some vertex space V inside, V is inside S. So this is XV, and here I have YV. So given any point here, I will take nearest point projection like that. Okay. And if I have some vertex space, some vertex V which is not inside S, so here is the schematic diagram. So what you do is that you take V bar to be the projection of the vertex V on the subtree S. So S is a subtree, it's a convex subset of T. So from any point there is a projection on this S. So given some vertex V not in S, so you first project this V to S. So maybe the projection is V bar, and W is the next vertex basically on this line. After V bar, this is the next vertex, and I'm calling the edge E bar. So now if I have some point above this V, inside some XV, if I have some point X, then what I do is that I mean, this is just so you, maybe I'll draw with the blue or something. So because there is very little space here. So over X, this is I'm inside X V bar, and here this image of X E bar is there, and here I have Y V bar. Okay, maybe I should not share this. This Y V bar. So then what I'm doing is that I am just projecting the shaded blue part on this part on Y V bar like that. This is what I'm doing. So by our assumption, this number 2, this assumption that whenever some vertex is going outside, then the projection is small and so on. So this will imply that the projection here is X, projection of X E bar inside Y V bar. Okay, so that will be uniformly small diameter. So what you can define it to be this map, maybe I just define it to be some X prime inside to be very precise. So here is like a choice involved. So this is small diameter, the projection is small diameter, you choose one like that. So this defines this map, and the proof that this is a coarsely Lipschitz retraction is very similar. So okay, so if somebody has seen the proof, this same, there is no difference. Okay, so yeah, so
Pranab, can you just remind us which case are you doing now? I mean, what was the hypothesis on this is not the bounded projection case, right? So what is the hypothesis here? I mean, this is for the subtree case that you are looking at, right?
So we are
some kind of a saturated.
So the narrow
it's
carpet
basically
is
your construct. Yes. So now what you're doing is you have a subspace of every vertex space, and the coarse intersection of adjacent vertex spaces is your edge space, yes. And you're constructing, a tree of subspaces rather than a subtree of spaces, correct?
Yes.
Yeah. And what you're proving now is that, and basically you're saying that the same sheet-wise nearest point projection onto these convex gadgets gives you some quasi-convex output. Yes?
Yes.
Okay.
Thank you. Yeah. But somebody who has not seen these things before, I'll just make a remark that this Lipschitz projection is not really the nearest point projection. It's very far from the nearest point projection. Okay. So once I have defined this, so these are like general framework. Okay. And now we will do another special case where we will define the paths. So namely, ladders. So what are these ladders? So ladders are basically these are kind of induced subtree of space where once again the vertex space and edge space will be intervals. Okay, so how do I define ladder? So what I do is that I will take some. I will start with some initial vertex space xu and a geodesic segment, finite geodesic segment here. Okay, and then whenever I see there is some edge space, then what I'll do is that I will project this. I'll project this thing on the corresponding edge space. Okay, so then I will go to the next. Yeah, so here there is some technicality. So if the projection has if I call this x bar and y bar, so if the distance between this x bar y bar is bigger than some universal constant d naught depending on this hyperbolicity and qi depending on those things, then what I'll do is that I will go to the next vertex space. Okay. And then I will join them by geodesic in the corresponding vertex space. So this is xv like that. Okay. So for all edge space that are coming into xu, I will project this x and y, and I will check their distance. And then if the projection distance is bigger than some threshold d naught, then I will go to the next vertex space, and there I will join by geodesic segment in that vertex space. If the projection distance is smaller than d naught, then I will not go in that direction at all. Okay, and then after I reach new vertex xv, again I do the same thing. So here if this edge is e, so I will look at all the edge spaces that are going into xv other than this e. So all the other edge spaces I will look at, and then I will project this blue segment on all these edge spaces, and I will follow the same formula again. If the projection distance is bigger than d naught, I will go into the next vertex space. If the distance is small, I will not go in the direction at all. So these ladders are built in this way inductively. So therefore you see that so what is this ladder? So ladder will be this union of all these geodesic segments. So there will be, so for the ladder there will be some subtree S inside this thing, and of course U is there. So you can call this U to be the center of this construction. So once you have that, and so then you have geodesic segments like this. Okay. And the interesting thing about this is that suppose I have to adjust in this thing. Okay. By our hypothesis that the length of the projection, the distance of projection is bigger than d naught, it will easily follow that this segment, so U is our central vertex. Okay. So this segment is uniformly close to this. So maybe I call them ladder, so I call it LU, this segment LV. So you can check that whenever I take a geodesic, let's say, starting from U, and let us say I have VI and VI plus 1, like this. So VI is closer to U than VI plus 1. So then what will happen is that this LVI plus 1 will be uniformly, this LVI plus 1 will be uniformly close to LVI, like that. So in this case, therefore, it will follow that given any point, I can draw a QI section, uniform QI section that will join this point to LU. So this is a very special property of this thing. So next, what I want to discuss is that how to join points inside ladders. So if I have a pair of points, how do I define a path which will be candidate for geodesic, quasi-geodesic? So that is done in first of all in the following special case. So ladders with narrow carpet. So this means that inside the ladder I have two QI sections. So this is my, maybe this is my central vertex. So this is LU. So then there are two QI sections, maybe say gamma 1, gamma 2, okay, contained inside the ladder, okay, which forms which are coming close at, I mean, at some point, okay, so that this part of the ladder, okay, where this gamma 1, gamma 2 are there, so that is a narrow carpet. So in this case, we can define geodesics joining any pair of points in the ladder. So what is the idea? So idea is that, so you see that whenever I have this narrow carpet, basically a posteriori, you know that this is a quasi-convex set, because you know that there is a uniform QI section through any point inside the carpet. So basically, this means that this carpet is a union of these QI sections, which are uniform quasi-geodesics, all are glued to this small diameter set. Okay, so there is a small diameter set, and then some quasi-geodesics are going out of it. The union of such a thing has to be quasi-convex, uniformly quasi-convex. So therefore, this carpet is a quasi-convex subset. If our space was going to be hyperbolic, so then this better be quasi-convex. So what you do is that we define natural candidate for nearest point projection on this carpet. So that's what I'm going to discuss. So retraction on the carpet. So what I do is that so given any point here, and I'll draw with red x. So what I do is that I know through this point x there is a QI section contained inside my ladder. So I'll draw that. Okay, and then I reach this LU. Now,
so here by a QI section, you mean a QI section that goes back to the root. Is that right? I mean,
yes.
It does not need to extend all over the place.
No,
correct?
no. Yes.
So it's just a quasi-isometric. I mean, it's actually just a QI quasi-geodesic. Is that right?
Yes, yes. So QI section over the U comma pi x basically. There's a QI section over this. So next to LU, you can connect by with QI section. And then what I do is that, so inside the carpet, I know through any point there is a QI section. So therefore, what I do is that I will just draw this dotted QI section contained inside the carpet. Okay. So if I drop these red lines on the tree, take the image under this thing. So how does it look? So it looks like this. So here there is U, there is X, and here maybe this is the vertex where I have small set like this. Okay. And so yeah, so now what I'll do is that I will look at this part. So over this geodesic in the tree, there are these parts of QI section that is going through X and a QI dotted QI section. Okay. So now we just look at the portion where this two QI sections are reaching the flaring threshold. Okay. So then you just define your this point on the dotted this QI section to be the projection. So this will be our X bar. So this is the candidate for this nearest point projection, and this is clearly it should be the nearest point projection once if you already have hyperbolicity. Okay, so that will be our QI section, and then what do I do? So given a pair of points, I draw QI section. I mean the projection on the carpet, and if I already see that these two QI sections are already closed somewhere, even before reaching the carpet. So then I will just go through this point along the QI section and jump to the other QI section and then go back. So that will be our quasi-geodesic. So if I had some Y here and some other path is here, and suppose this is already closed here, so then you don't have to go to the projection. I mean, so you just go like this. This will be a path. So otherwise, what you do is that otherwise you go from X to X bar, Y to Y bar, and inside the carpet you join X bar, Y bar by geodesic. So already we have described quasi-geodesic inside the carpet. So your path joining X, Y will be X to X bar, there is a QI section, Y to Y bar, there is a QI section, and then geodesic in the carpet joining X bar, Y bar. So that will be your candidate for the quasi-geodesic in this special ladder. Okay. And as before, just like the metric bundle situation, the general ladder case is you just need to break the whole ladder into small ladders. I mean, these special kind of ladders. If I so if I call this special ladder, so what you do is that you have here is a segment inside some vertex space, and then you have this ladder thing. Okay, so then what you do is that you can decompose this into sub ladders. So you can find points here. Okay, on the so this is my central vertex, and you can form sub ladder. Okay, like that, and so such that these sub ladders are special ladders like this. They have narrow carpets. Okay, and so the construction again, this will imply that the QI section through these points, these QI sections inside this thing are uniformly co-bounded. Okay, so what do I do? So what I do is that I will just maybe I start with this vertex, so maybe call it X or something, and then I will go along this geodesic vertex space geodesic alpha, and just see if I check this point. Okay, check something, maybe start with this point, and you form the ladder inside this. So ladder is a special kind of trio space. So inside this, I can construct a ladder. Okay. So I'll take this segment, I form the ladder. I check this property satisfied or not. That is, this ladder has a small, I mean, this narrow carpet. If this is satisfied, I will leave this point. I'll go to the next point, and again I'll check that. And after a certain time, maybe I will reach at a position where I don't have this property anymore. So then I will just take that point, and I will take the corresponding subladder, and then I will take the next part of this alpha and again do the construction and so on. So by construction, then it will follow that this part through these points, these are uniformly co-bounded, and in this case, the geodesics is simply so. So if I have this is like this is my narrow carpet. So how do I join some point here and here? So it is just that you go along this and just say where this flaring threshold is.
Sorry, Pranab, I did not quite. What are the black lines supposed to indicate? They are just QI sections from the endpoints of your alpha or maximal? Yes. What?
Yes. They are QI
so
sections.
what is? Yes. What is alpha? I mean, how do you identify alpha? I missed that.
Is a geodesic segment in the vertex space XU.
Yes, but I mean, so you can do this for, suppose you can do this for every point. I mean, is alpha some maximal subsegment or what exactly is it?
Alpha is some arbitrary geodesic segment in XU.
No, but it has been extended to, I mean, it is part of a geodesic subsegment of some geodesic, is it not?
No, XU is a vertex space. Alpha I am taking to be some geodesic segment inside XU. Once you have that, so maybe I should have forget about this alpha. This is my LEU. Okay. So now, given this segment, I can form the ladder, but the ladder may not have this property, this special property. So then, what I do is that I will find sub ladders inside this that will have.
I see. Okay, fine.
So the black lines may not be defined on the full subtree of this.
Yeah, that was what I was worried about.
This will be defined on some smaller subtree. Okay, so if you project the whole ladder, that is a bigger tree maybe, and these black things are smaller, defined over a smaller subtree. Okay, but these will be, by construction, these will be uniformly co-bounded. So now again, so because we already know geodesics in the special ladders, and therefore we now invoke our description of geodesics for the strongly asymmetrical situation. So this is like decomposing the ladder into that kind of tree of space where the tree is a finite segment and then these black things are really the edge space and co-bounded and so on. So this will give a kind of inductive description for geodesics inside the ladders. Is it okay? So the next thing that
say that again. What is the inductive description that you're referring to?
Well, so what I'm saying is that in the special ladders, we know the geodesics. We have described the geodesics. And for the general ladder, we have decomposed it into sub-ladders, special sub-ladders. And this is like the description of this strongly acylindrical tree of space, because these
I see.
black lines are co-bounded. Okay.
I see, I see,
So
I
if
see.
I have to join
So,
some
so
point,
is it something analogous to this thing where you pick sections which come close at a specific part, and then you're decomposing a long chain of ladders into, um, I mean, basically, what is it? So you have two sections, say, of the base space, and then you look at parts where two of these guys come very close, and then you cut that part off and then proceed to construct another one. And then there are these sort of isolated regions, co-bounded regions, where
yes.
two adjacent sections come very close. But the area where they come close, this sequence is co-bounded. Is that, this is the analog in the ladder
Yes.
case? Is that,
Yes.
yes?
Yes. So just like I was drawing here, so if I have to, so I know the black things are co-bounded. So, but what are the geodesics joining them? So if I have some point here and some point here, so what I do is that I will look at this segment, and with this carpet, I will just see where these things are close. Then I'll go along this, and then again I'll see where these are close, and then I'll join this. So these will be our paths joining these points. Okay, so I have only a few minutes left. So what I do is that I define this what is called the flow space. So given a vertex space, we define what is called the flow space, and for every constant k sufficiently large, we define the k flow. So this simply means that we do something similar to this. So what we do is that we have this xv, okay, and maybe the next vertex space is xw. So then, so so look at this whole object, this space over this VW, this whole thing. So we know by our first case that this whole space is hyperbolic, and then XV, XW are quasi-convex in this thing. So what you do is that you to define this flow space. Okay, so suppose yeah. So then. So like the flows, like this ladder construction, the flow space will be also similar. It will be induced subtree of space, okay, and so therefore for every point in the base, for this will be subtree of space. So for every point in the base, there will be some. I mean, for the subtree, there will be some QI embedded subset and so on. So if I have some vertex space W, so then so my so this will be some tree of space, right? So YV is simply XV. So YV will be simply XV, and if there is some next vertex space, okay. So maybe I call it something Z. Okay. So then what will be the corresponding thing in the XZ? So what we will do is that yeah, so sorry, YW is simply this quasi-convex set. Okay, so maybe this is XE. So then you can say something like XE, image of XE inside your this thing, and then to define the corresponding subspace inside XZ, what we do is that we project this red portion, this portion, okay, on the XZ. Or you can just say you take the projection of this thing on this corresponding H space, okay. Take the projection, go here, and here this projection is a quasi-convex set, but you want a geodesic space, a QI embedded subset. So what you do is that you take a sufficiently large neighborhood. Okay. So this is the way you define, just like the ladder construction. So you start with the full space, you project, keep on projecting, okay. And as long as the projection has large diameter, so you take the image and then you take a quasi-convex hull, basically. So what you do is that
So essentially what you're doing is you're doing this ladder construction, but now with full sets rather than with geodesics.
Yes.
Is that correct?
Correct. Yes. So this will be your flow space, and as Manda said, so this is very similar to ladder construction, and in this case also you can easily show that even any point in this space, there is a uniform QI section starting from that point and ending in the XV. Like that. Okay, and so therefore in this case what you do is that given a pair of points, so you pass the QI section and that will come to XV, and through both the points you take QI sections that will come to XV. Okay, and then so let us say I have some point here somewhere and some point here somewhere. So I draw QI sections through these points, and I will come here and here. Okay, so then I will take this segment. Okay, and I will define a ladder using this segment. Okay, so if I call this geodesic segment lambda, so using this lambda, I will define a ladder inside my flow space. Okay, so flow space is a tree of metric space on its own right. So I will define a ladder, but I have to be slightly careful here. Only thing is that I have already these two blue QI sections. So what I'll do is that whatever these blue things are there, I will not disturb. So like in this picture, I have this segment here. So in the XW, so I will not disturb at all. And so wherever I have this common part of these blue sections, blue QI sections, I will not disturb. What I'll do is that I'll go in the orthogonal direction. I will change. So that means if I have some H space here, so then this blue segment inside XW I'll project there, and then I will do the same construction. So we are doing in the flow space. So I'll project into the corresponding H space. If the projection has large distance, then I will go to the next vertex and so on. In this way, I'll form something like a ladder inside the flow space. Okay, and which will contain both these blue QI sections. Okay, so given any pair of points XY, I will define like that, and then we know how to define geodesics in the ladders. So so therefore we can join points. I mean in flow space Y also uniform quasi. So this one has to show that these are uniform quasi. So this is the last technical part of this proof, where actually you have to construct paths and check all the properties and so on, and you have to do it in break it into so many cases and so on. So these are kind of long proofs and so on. So after this is done, so what we do is that we use this as a black box, and then given any pair of points, basically, so then we break this. So I'll be very rough and so on. So here, so if I have 2 points over XU and XV, which are very far, maybe. Okay, so then what we will do is that so this is sorry, this is U, this is V. So I take the inverse image of UV. So this will be a chain of this vertex spaces, and I will flow this in every direction. Okay, and then this flow space I will break it in such a way where we have kind of description of this quasi geodesics using this as a black box. So there is a kind of clever way of decomposing this general flow space into this kind of vertex space flow space, and so in the vertex space, I mean the vertex space flow, we know quasi geodesics. So therefore, in general, we also know quasi geodesics. So I think the time is over, so I cannot explain more. So I think I'll just stop. So I don't know.
Thank you, Pranab, for this wonderful and instructive talk. So, any questions for Pranab?
Yeah, so this last bit that you were saying, Pranab, so what you're doing is here you have defined the flow space of a vertex space, and essentially what you sketched was a proof that the flow space of a vertex space is QC. Is that right?
Yes.
And what was the last bit that you were saying, that the flow space of some arbitrary thing is can be decomposed into flow spaces of vertex spaces?
So now, so the next thing will be to do is that suppose I have two flow spaces. and
Yeah.
the intersection is non-empty. So then
Yes.
so this proof shows that these are the quasi-geodesic and this space is hyperbolic flow space. Now suppose I have two vertex spaces and whose flows are intersecting somewhere. So
Yes.
then we will show that the union of these two things are also hyperbolic. And so basically
Yes.
then to describe the quasi-geodesic, what you do is that you have these two kind
No,
of
but then I mean, what I don't understand is if you have two of these guys, then both should be in the same flow space, no? I mean, if it intersects, if two of these guys intersect in a vertex space and you take that vertex space and flow it, you're going to get the, I mean, you are allowed to, once you have flowed the first vertex space into this guy, oh, no, I mean, the flow spaces themselves intersect. Is that what you're saying? Or,
yes.
okay. Okay. So the intersection of the flow spaces, is that also sub flow space? I mean,
So that will be some kind of subtree of space. Yes.
no, it's a subspace. Yeah, it's a tree of subspaces.
Tree of space.
Maybe a subtree of subspaces. Yes?
Yes.
Okay. And that guy is quasi-convex in both. So you can paste them. I mean, yeah, is that the point?
Yeah, that is the point.
Yes?
Yes.
Okay, and there's some uniformity so that you can keep on chaining these things together. Is that what
Yes.
you're
That
saying?
is basically that.
So yeah, and okay, so what is the, at the end of the day, what do you get? Suppose you have this whole collection of flow spaces that you have glued together
Okay,
by
that I thought, okay, so
No, you don't have to write, just say in words. What exactly
okay,
are you trying?
so you have XU, XV, and maybe their flows are not intersecting at all. So what you do is that you flow this wherever as much as possible along this
Yes,
geodesic. So both are
yes,
flowing. Okay. And then
yeah.
you reach somewhere, you start flowing that and so on.
Hmm.
I mean, there is a clear way of doing this. So basically, given this,
No. I mean, what is the upshot? At the end of the day, what do you get? So after you have flowed all this stuff as much as you like, what is the end result?
okay, so basically, therefore, given this vertex A, U, and V, so you are
Yeah,
breaking this interval U, V into subintervals, basically.
yeah, yeah,
So roughly speaking, so for each subinterval, there is a point in the subinterval, such that for that vertex space, it is flowing fully to all the vertex
yes,
in the
yes.
like that. So those things are for them you can basically draw geodesics. Okay,
Oh, I
and
see. I
given this
see.
subinterval,
Yeah,
let us say u prime v prime, what will happen
yeah,
is that this x u prime and x v prime, the flow of
yeah,
those, they are not
yeah.
intersecting and they're bounded.
I see.
So then we use again the strong aesthetical this thing.
I see. Okay, okay. Very good. Thank you. Thank you. Yeah.
Any other questions for Pranab? So if not, let's thank our speaker again for this wonderful talk, and we'll see you next week. Thank you, Pranab. And